This is the section that gets people a little bit mixed up. It can be hard to wrap your head around some of the things that are included in this section, but it's the continuing of the logic of compound statements. All right, this one we're going to deal with conditional statements. Okay, a conditional statement is a statement where P and Q are statement variables, and it's in the structure of if P then Q, or P implies Q. It's denoted by the right arrow pointing from the hypothesis or antecedent to the conclusion. It is only false, this statement is only false if P is true and Q is false. Otherwise, it's true. Oh, okay, I'm sorry. A conditional statement that is true by virtue of the fact that the hypothesis is false is sometimes called vacuously true or true by default. So if the hypothesis is false, then the overall statement is still true. That's the part that can throw people off a little bit. Consider the statement as an example. If 0 equals 1, then 1 equals 2. Both are false. But when you consider the conditional, it's actually true. It's vacuously true. If 0 equals 1, which is false, then 1 equals 2, which is also false. So it, logic-wise, ends up being true. That whole statement is true because if 0 did equal 1, 1 would equal 2. But it's not, but neither one is true, so the whole statement is true. It's, like I said, it can be a little bit to wrap your head around. Since the hypothesis of the statement is false, the statement as a whole is true. So this is the truth table for the conditional structure. Like I said, it is only false when the hypothesis is true and the conclusion is false. That is the only time the conditional is false. Otherwise, it is true. Okay. In the expressions that include the conditional as well as other logical operators, the and, or, and not are performed first, and the conditional is performed last. So it is the lowest priority in the order of operations. Okay, so construct a truth table for the statement form P or not Q implies P, not P. Okay? So how would you do that? You would add parentheses accordingly to indicate order of operations. Then fill in the 4 possible combinations of the truth values for P and Q. Then enter the truth values for not P and not Q, and fill in the P or not Q column, and then the conditional. So this is the truth table that you would end up with. All right. So the hypothesis, conclusion, and then the resulting truth table, which, if you look at it, matches, it happens to match not P, the truth values for the whole statement, and not P are the same. So that statement could be reduced to just simply not P. Okay. Logical equivalences involving the conditional. This got screwed up here. This program is not showing the slide the way it should be. It should be use truth tables to show the logical equivalence of the statement forms P or Q implies R, and P implies R or Q implies R. So you probably need to write that down and make a note of that when looking at the notes from this. And if you look at the slide online, which will be posted this afternoon, it should, if you pull it up in PowerPoint, it should be represented properly. But there's 8 possible combinations of the truth values for P, Q, and R. Then this is getting mixed up again. Fill in the columns for each element of the statements. And then on each side, and you come up with this monster truth table. P or Q and implies R, and P implies R or Q implies R, you can see that the truth values in the result, the 2 columns are in fact the same. So let's see here. They are logically equivalent. Now, you can represent an if-then structure with an or with the or operator instead. So, for example, you rewrite the following statement in the if-then form. Either you get to work on time or you are fired. If you don't get to work on time, then you will be fired. Pretty simple. If you're not to work on time, you get fired. Then you get fired. So let not P be you get to work on time, and Q be you're fired. Then the given statement is not P or Q. You do not get to work on time. Also P is you do not get to work on time. So it's negating the positive So the equivalent if-then version of P implies Q is if you do not get to work on time, then you are fired. So it's just a matter of getting the wording right. And like I said before, this is fairly common sense. If you inject statements into the variables and write it out or express it in terms of common statements, you can make sense of what is being represented in variables. The negation of a conditional statement. All right. By definition, P implies Q is false if and only if its hypothesis is true and its conclusion is false. So it follows that the negation of if P then Q is the logical equivalent to P and not Q. This can be represented symbolically as this here on the screen. It's one way to get rid of the conditional out of a logical statement. If you run into this negation of a conditional, you can substitute it with P and not Q. So the equivalence is maintained. You can also start from the logical equivalent of P implies Q is equivalent to not P or Q. Negate both sides. Use De Morgan's law to change the operation and the signs. And then with double negative, it becomes P and not Q. So write negations for each of the following statements. If my car is in the repair shop, then I cannot get to class. What would be the negation of that? That's just restating the statement, not the negation of the statement. What's the opposite of that? What would be the negative of that? My car is in. My car is in the repair shop, and I can get to class. It's the negation. It's the opposite of what the original statement is. Now, the opposite of if Sarah lives in Athens, then she lives in Greece. Well, Sarah lives in Athens, but she doesn't live in Greece. She lives in Athens, Georgia, as an example. So that you negate the second. If you convert it to an and, you negate the conclusion. So my car is in the shop, and negate this, I can get to class. And Sarah lives in Athens, and she does not live in Greece. You negate just the second argument. So, yeah. Now, this is a kind of a weird one. the contrapositive of a conditional statement. The contrapositive is the equivalent to a conditional statement. If P then Q is equivalent to if not Q, then not P. So the contrapositive of that statement about the car being in the shop, okay, if my car is in the shop, then I cannot get to class. The contrapositive would be if I can get to class, then my car is not in the shop. You invert and reverse the variables in the statement. It's if P then Q is equivalent to not Q, if not Q, then not P. They are logically equivalent. So they can be substituted for each other. It is, like I said, logically equivalent to its contrapositive. The following statements in contrapositive form. If Howard can swim across the lake, then Howard can swim to the island. If Howard can't swim to the island, then Howard can't swim across the lake. Which logically makes sense. If he can't make it to the island, he can't make it all the way across the lake. If today is Easter, then tomorrow is Monday. If tomorrow isn't Monday, then today can't be Easter. Right? Yeah? Yes. Yeah, just another way of stating the same statement. Invert and reverse the statements. And yeah, like I said, if Howard cannot swim to the island, then Howard cannot swim across the lake. I'm sorry, go back?
No, just hold the solution.
Oh, okay, yeah. If tomorrow is not Monday, then today is not Easter. All right. Good?
Almost.
Okay. All right. So now the converse and inverse of a conditional statement are not equivalent to their original conditional statement. The converse of a statement is if P implies Q, the converse is Q implies P. The inverse is not P implies not Q. All right. So the converse just flips the arguments of the implies operator, and inverse just flips the inverts the individual statements. These are not logically equivalent. You could see this intuitively with the statement, if Howard can swim across the lake, then Howard can swim to the island. Okay. The converse would be, if Howard can swim to the island, Howard can swim across the lake. That's not necessarily true. So it's not logically equivalent. The inverse would be, if Howard can't swim across the lake, then Howard can't swim to the island. Again, not necessarily true. He might have enough energy to swim to the island, but not enough energy to swim across the old lake. So that is not logically equivalent. Likewise, the converse of, if today is Easter, then tomorrow is Monday. The converse would be, if tomorrow is Monday, then today is Easter. Again, not necessarily true. The inverse would be, if today isn't Easter, then tomorrow isn't Monday. Again, intuitively, you know that that's not necessarily true. So, converse, here's the resulting statements. Converse and inverse, therefore, are not equivalent to the original statement. The converse and the inverse of a conditional statement are logically equivalent to each other. So the converse and the inverse are equivalent. So if a operation requires both or either the converse or the inverse, you can use either one. All right. Only if and the biconditional. If P and Q are statements, P only if Q means if not Q, then not P. Or equivalent. The typo in the thing is supposed to be if not P, then not Q. Or not Q, then not P. That's just the conditional right there. I've been running into errors with these slides the more I get into the course. But this is supposed to be equivalently, if not P, then not, or if not Q, then not P. So, rewrite the statement in if-then form if in two ways, one of which is the contrapositive of the other. John will break the world's record for the mile run only if he runs the mile in under 4 minutes. In one way, that would be if he runs the mile if he does not run the mile in under 4 minutes, then John will not break the world's record for the mile. That would be the contrapositive. Invert the statements and reverse the order of the individual statements. Version 2, if John breaks the world's record, then he will have run the mile in under 4 minutes. So it goes both ways. It can go either way. Now the formal definition, given statement variables P and Q, the biconditional of P and Q is P P, if and only if Q, is denoted by the double-ended arrow between P and Q, is only true if P and Q have the same truth values, and it is false if P and Q have opposite truth values. The words if and only if are sometimes abbreviated IFF. I've rarely seen that, but it's out there, so there you go. And I forgot a stylus. You have a pen that I could borrow? Or an extra?
Okay.
Yeah. With a retractable tip. Yes, perfect. All right. Now the truth table for this, you can see if P and Q match, the biconditional matches. Now, one thing that will not be covered in digital logic, and those of you that have taken digital logic will vouch for me on this, I'm sure. This is the equivalent to, whoops. That is an XNOR gate. It is a gate that's used for equivalence in digital logic. Huh?
You said what gate?
XNOR. It's the same truth table as, oops. As the biconditional. So if you're comparing two binary values, you just have XNORs comparing each bit, and if they're all true, then the binary numbers are equivalent. It's the one gate that you don't learn in digital logic. I'm not sure why, but there it is. But yeah, it's the same truth table. But all right. Oops. Come on. Okay, there we go. Okay. The biconditional is co-equal with the conditional as far as order of operations is concerned. So they are both the lowest priority on the order of operations. Let's see here. If they both exist in the statement, in a compound statement, you might need to use parentheses. Okay, so this is the full hierarchy of operations for logical operations and for the order of operations. Not inversions are first, and an or are next, then the conditionals. All right. Oh, sure. Yeah. All right. Now rewrite the following statement as a conjunction of two if-then statements. Let's see here. Okay. Okay. If the computer program is correct if and only if it produces correct answers for all possible sets of data. So two if-then statements, conjunction would mean an and. So the computer program is correct and it produces correct answers for all possible sets of input data. Okay, what would the other conjunction be? If the program is correct, then it produces the correct answers for all possible sets of data. And if this program produces the correct answers for all possible data, then it is correct. So, and next is necessary and sufficient conditions. If R and S are statements, if R is a sufficient condition for S, means if R, then S. If it's a necessary condition for S, it means if not R, then not S. So that would be the inverse. If not R, then not S, right?
You have a slide.
I'm sorry?
Stay on the slide, please.
Yeah. Okay. So rewrite the following statement in the form of if A, then B. Pia's birth on U.S. soil is a sufficient condition for her to be a U.S. citizen. If she's born on U.S. soil, then she's a U.S. citizen. All right. Yeah, pretty straightforward. We've done conditionals already. Use the contrapositive to rewrite the following statement in two ways. George's attaining age 35 is a necessary condition for his being President of the United States. So the contrapositive would be invert the statements and reverse the order. So if he is not able to be, let's see here, contrapositive, okay. Oops. Come on, cooperate. If George has not attained the age of 35, then he cannot be President of the United States. Or if George can be the President of the United States, he has attained the age of 35. Just different ways of rewriting the same thing. There we go. A little bit bigger there. Come on. You're not. Is that everything? Oh, that is everything. That's the last of the slideshow. All right. So, a lot to wrap your head around with for conditionals. Not all of it is completely intuitive, especially the vacuously true conditional entry. If the hypothesis is false and the conclusion is also false, the overall statement is still true. So that's the kind of the hard to wrap, some people have a hard time wrapping their head around that. So let's see here. No. Let's see here. And I continue the logic of compound statements with, come on, why aren't you? No. All right. Valid and invalid arguments. What can you do with all this logic and all these structures that we've learned so far? We can create valid or invalid arguments. Or create valid arguments and identify invalid arguments. An argument, by definition, is a sequence of statements. All statements in an argument and all statement forms in an argument form, except for the final one, are called premises, or assumptions, or hypotheses. The final statement is called the conclusion. The symbol with 3 dots here is read as therefore, normally is placed just before the conclusion. To say that an argument form is valid means that no matter what particular statements are substituted for the statement variables in its premises, if the resulting premises are all true, then the conclusion is also true. To say that an argument is valid means that its form is valid. All right. Testing an argument form for validity. Identify the premises and conclusion of the argument form. Construct a truth table showing the truth values for all the premises and the conclusion. A row of the truth table in which all premises are true is called a critical row. If there is a critical row in which the conclusion is false, then it is possible for an argument of the given form to have true premises and a false conclusion, and so the argument form is invalid. If the conclusion in every critical row is true, then the argument form is valid. So, I'll see how that looks on a truth table in just a minute. Let's see here. Determine whether the following argument form is valid or invalid by drawing a truth table indicating which columns represent the premises and which represent the conclusion with a sentence of explanation. Okay. When you fill in the table, you only need to indicate the truth values for the conclusions in the rows where all the premises are true, the critical rows. Because the truth values for the conclusion of the other rows are not relevant for the validity or invalidity of an argument. So let's look at this. P implies Q or not R. And if this is true and this is true, Q implies P or R, then therefore P implies R. So if this is true and this is true, therefore this is true. If all entries in the truth table for those conditions and statements are true, then the argument is valid. The truth table shows that there are many situations where in which the premises and the conclusion are true, but there is one situation where the conclusion is false. Therefore, the argument is invalid, as shown by the truth table. Remember, the critical rows are the premises that have all true values. These entries here, these rows, are irrelevant because the premises are not all true. But we see that true, true, and true here, but the conclusion is false for this combination of inputs, values for the component statements. So the argument is invalid. I found another error in the slides for this. In this little section here, modus ponens and modus tollens. An argument form consisting of two premises and a conclusion is called a syllogism. Bonus points if you can pronounce it right. The first and second premises are called the major premise and the minor premise, respectively. The most famous form of syllogism in logic is called modus ponens. It has the following form. If P then Q, and P, therefore Q. So if P implies Q and P is true, then Q is true. So here's substituting for statements for the P's and the Q's. If the sum of the digits of that number is divisible by 3, then that number is divisible by 3. And the sum of the digits of this number is divisible by 3, therefore the number is divisible by 3. So that's modus ponens. Modus tollens gets skipped. There's missing a slide on modus tollens. So we'll revisit that in just a minute. Use modus ponens or modus tollens to fill in the blanks of the following arguments so they become valid inferences. If there are more pigeons than there are pigeonholes, then at least 2 pigeons roost in the same hole. There are more pigeons than there are pigeonholes, therefore, at least 2 pigeons roost in the same hole. That's modus tollens. Modus ponens. Modus tollens is is I believe the contrapositive of modus ponens. So if this number is divisible by 6, then it is divisible by 3. It's not divisible by 3, therefore that number is not divisible by 6. It's the contrapositive. It's of modus ponens. Modus tollens is. If P then Q and not Q, then not P. If P then Q and not Q, then not P. So it'll be on a chart toward the end of the slide deck here. Yeah, so that's the result. At least 2 pigeons roost in the same hole, and that number is not divisible by 6. So, additional valid argument forms, rules of inference. A rule of inference is a form of argument that is valid. Thus, modus ponens and modus tollens are both rules of inference. The following additional examples of rules of inference that are frequently used in deductive reasoning. Generalization. If P is true, therefore P or Q is also true. And if Q, then P or Q is also true. So that's generalization. That's adding a variable to an argument. Let's see here. As an example, counting upperclassmen at your school. You ask what class Anton is in and are told he's a junior. Therefore, if Anton is a junior, then more generally, Anton is a junior or a senior, which might have use in some sort of argument, but it means he's an upperclassman. Knowing that upperclassman means a junior or senior, you can add Anton to your list if in your counting. But and then specialization. If P and Q are true, therefore P is true. If P and Q are true, then Q is true. Therefore Q is true. Because both sides of the and have to be true for this statement to be true. You can specialize and say, let's see, you can get rid of the extraneous information, like Anna knows numerical analysis and Anna knows graph algorithms. In particular, Anna knows graph algorithms. So you can eliminate extraneous information by this rule of inference. So elimination. These following arguments are valid. If P or Q and not Q, therefore Q, and not Q is true, therefore P is true. Because in an OR statement, if one is false, the other one has to be true for the OR statement to be true. Right? So, as an example, if x minus 3 equals 0 or x plus 2 equals 0, but you also know that x is not negative, so x plus 2 is not equal to 0. Therefore, by elimination, you can conclude that x minus 3 equals 0. Because this one is not true. The other one has to be true. Transitivity. If P then Q and P then R, then P implies R. So this is a chain of if-then statements. and you can go train these along and chain these along into whatever length is necessary for your argument. But if P implies Q and Q implies R, then therefore P implies R. So this example, if P is divisible by 18, then N is divided by 9, divisible by 9. If N is divisible by 9, then the sum of the digits of N is divisible by 9. Therefore, if N is divisible by 18, then the sum of the digits of N is also divisible by 9. The proof by division into cases. The following arguments forms are valid. If P or Q, and P implies R, and Q implies R, therefore R. It happens that you know one thing or another is true. If you can show that in either case a certain conclusion follows, then the conclusion must also be true. Okay? So this is the example that they give. If x is positive or x is negative, if x is positive, then x squared is greater than 0. If x is negative, then x squared is also greater than 0. Therefore, x squared is greater than 0 because x is either positive or negative, not 0. Therefore, x squared is greater than 0. All right, let's see here. How are we doing here? Okay. Here's a little bit more complex example. You're about to leave for class in the morning and discover that you don't have your glasses. You know the following statements are true. If I was reading my class notes in the kitchen, then my glasses are on the kitchen table. If my glasses are on the kitchen table, then I saw them at breakfast. I did not see my glasses at breakfast. I was reading my class notes in the I was reading my class notes in the living room, or I was reading my class notes in the kitchen, one or the other. If I was reading my class notes in the living room, then my glasses are on the coffee table. Where are the glasses? They would be on the coffee table. You can use intuitive logic for that. You didn't see them. It could because you didn't see glasses at breakfast. They're not in the kitchen. And if you were reading, therefore you were in the living room. Therefore the glasses are on the coffee table. More formally, let these variables mean the various potential substatements of the deduction. Okay? RK implies GK. If I was reading notes in the kitchen, then my glasses are on the kitchen table. Okay? GK implies SB. If my glasses were on the kitchen table, then I saw them at breakfast. If I was reading in the kitchen, I saw them at breakfast. Okay, that's one conclusion. Now, if I was reading in the kitchen, and I saw them at, that means I saw them at breakfast, but I didn't see them at breakfast, so I wasn't reading by modus tollens. I was not reading in the kitchen. Now it's by the initial givens, I was either reading in the living room or reading in the kitchen, one or the other. I was not reading in the kitchen, therefore I was reading in the living room by elimination. Okay? If I was reading in the living room, then the glasses are on the coffee table. I was reading in the living room by the conclusion of the previous argument. Therefore, by modus ponens, the glasses are on the coffee table. Deductive reasoning. And now we deal with fallacies. A fallacy is an error in reasoning that results in an invalid argument. Three common fallacies are using ambiguous premises, circular reasoning, and jumping to a conclusion without adequate grounds. Let's see here. In this section, we'll discuss two other fallacies called converse error and inverse error. They superficially resemble those that are valid, but are not, in fact, valid. We can show that an argument is invalid by constructing a truth table for the argument form and finding at least one critical row, in which all the premises are true, but the conclusion is false. Another way is to find an argument of the same form with a true premise and a false conclusion. For an argument to be valid, every argument of the same form whose premises are all true must have a true conclusion. It follows that for an argument to be invalid means that there is an argument of that form whose premises are all true and whose conclusion is false. All right. Show that the following argument is invalid. If Zeke is a cheater, then Zeke sits in the back row. Zeke sits in the back row, therefore Zeke is a cheater. That's not true. Not necessarily. Are the back rows cheaters? No? Okay. Just checking. You can recognize that that's not a valid argument intuitively. But one can imagine a person who is not a cheater happens to sit in the back row. Then if that person's name is substituted for Zeke, then the first premise is true by default, and the second premise is also true, but the conclusion is false. Generally, the general form of the previous argument is P implies Q, and Q, therefore P. This is not always the case. This is not a valid argument. Consider the following argument. If these two vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, therefore these two vertices have the same color. Not necessarily. It looks like modus tollens P implies Q, not P, therefore not Q. Not a valid argument. That's the form that this argument takes. So watch out for that as being a invalid argument for doing proofs. The following argument is valid by modus ponens, but its major premise is false, and so is its conclusion. If Canada is north of the United States, then temperatures in Canada never rise above freezing. Canada is north of the United States, therefore temperatures in Canada never rise above freezing. Well, this is false, so therefore the whole argument, you can't trust this to be true as well. The only part of this argument that's true is the Canada is north of the United States. So converse error, but has a true conclusion. Argument is invalid, but the conclusion is true. If New York is a big city, then New York has tall buildings. New York has tall buildings, therefore New York is a big city. Not necessarily. Jackson has tall buildings, but it's not a big city. So it's not a valid. If you substitute Jackson for this, then the first premise is not true. Jackson has tall buildings is true, but the conclusion, it would be false. Jackson is not a big city, at least by most people's standards. An argument is called sound if and only if it is valid and all its premises are true. An argument that is not sound is called, of course, unsound. The important thing to note is that validity is a property of argument forms. If an argument is valid, then so is every other argument that has the same form. Similarly, if an argument is invalid, then so is every other argument that has the same form. Contradictions and valid arguments. The contradiction rule. If you can show that the supposition that statement P is false leads logically to a contradiction, then you can conclude that P is true. Okay? So, if not P implies C, therefore P. We'll see that as if not P implies C, then it is true. The premise is true. The conclusion is true. Because P is the opposite of not P. The logician Raymond Smullyan describes an island containing two different types of people: knights who always tell the truth and knaves who always lie. You visit the island and are approached by two natives who speak to you as follows. A says B is a knight. B says A and I are of opposite type. What are A and B? Can you figure it out? Knights always tell the truth. Knaves always lie. They are both knaves. They are both lying. To see this, the reason as follows. What A is true, what A says is true, therefore B is also a knight, assuming A is a knight. What says is true, but A and B are opposites if what B says is true. We have arrived at the contradiction. A and B are both knights, and A and B are of opposite type. Therefore, the supposition is false, and A is not a knight. A is a knave. What A says is false, therefore B is not a knight, and B is also a knave. And I believe we got just summary of the rules of inference. Take a picture of this. This is the various ways of conducting an argument or constructing an argument. The different rules of inference. I understand we're running short on time. I believe this is the last slide. Yeah, this is the last slide, so I'll leave that up and return your pen. But that should be wrap it up for the day.